construction staging of the superstructure up to the modeling of our abutments, our piers, to our pile caps, and to our piles, it can be modeled in one single model. It can be modeled, analyzed, and designed in one single file. So apart from this, here are some of the MIDAS Civil's
The webinar will
advantages.
begin shortly. Please remain on the line.
So MIDAS Civil boasts its simple and smart working environment. So we have user-friendly graphic user interface. We have 3 menu, and all of our tables are Excel compatible. So you can easily use it for cross-referencing of your data. Aside from it, MIDAS Civil has wizard for various types of bridges. So what you can see here is the simple ones, which are the truss wizard and the beam wizard. So from the simple ones, we also have this one, the FCM bridge wizard, or the different bridge wizards, which includes the
The
simulation
webinar will begin
of
shortly.
different
Please remain on the line.
construction types. So this one is for the free cantilever method of segmental bridge. Then this another one is for the incremental launching method of bridges. And these two, cable stayed and suspension bridge wizard, are also included in the wizard for our MIDAS Civil. So in this wizard, you can automatically make the layout, the tendon layout, the section, the loads, and the construction stages of your bridges. So aside from it, we have quick generation of strands or tendons using our tendon template.
The webinar will begin shortly. Please
So
remain on the line.
depending on the section database that you are using, we already have some of the auto generation function for it. For some, you can just use our other features for adding tendons, such as the modification of tendon and the tendon template. And also, you can import from the XF to MIDAS Civil for your tendons. MIDAS Civil also boasts its effective simulation of construction stage analysis. So, construction stage analysis reflects the time-dependent material properties and pre-stress conditions. The
The
intermediate
webinar
and
will
long-term
begin
pressure
shortly.
pre-stress
Please
losses
remain
of
on the
components
line.
are being simulated with respect to its time factor. And also, generation of all results for each stage is shown in MIDAS Civil. Also, the camber can be easily generated using MIDAS Civil. You can also optimize moving load analysis. So aside from an ASH to LRFT, you can optimize the moving load according to different moving load codes. So we have the influence lines and surfaces. And then you can combine member forces to check
The
the
webinar will begin
availability of
shortly.
corresponding
Please
force
remain on the
components
line.
depending on the maximum and minimum effects. So MIDAS will also have comprehensive seismic analysis. So MIDAS will already incorporated DPWH, LRFD, BSDS in our software. So all you need to do is input the site-specific factors for your bridges. So the PGA, SSS1, and the response modification factor, which is already given in our local codes, can be inputted in our software already. And here are some of the analysis capabilities of our software.
The
Aside from the
webinar will
static
begin
analysis,
shortly.
we have the
Please
dynamic
remain on the
analysis,
line.
which includes the response spectrum analysis, time history analysis, and then the free vibration analysis. It also has geometric nonlinear analysis,
The broadcast
which
is now
includes P
starting.
delta
All
analysis
attendees
and
are
then
in
large
listen-only
displacement
mode.
analysis. For some parts of your bridges, it has structural masonry analysis, which is under the material nonlinear analysis. And also for your steel bridges, you can also include the lateral torsional buckling or the linear buckling analysis. And it also includes the time transient analysis for your pipe bridges. And also heat of hydration analysis is also available in our software. Advanced analysis such as pushover analysis and boundary nonlinear time history analysis can also be performed in our software. Different database of dampers, isolators, gaps, and nooks are available already in our software. For cable stayed bridge, we have separate analysis for that, which is known as large displacement analysis and the unknown force by optimization. So this can be very beneficial for those who are modeling or designing bridges such as this, suspension and cable stay. So other analysis includes our moving load analysis and settlement analysis. Good day, everyone. Welcome again to another webinar brought to you by Midas IT Philippines. This is China Riano, your technical support for Midas CU. So, for today, we will be talking more about the box culvert, from box culvert modeling to analysis up to its design. So, let me give you a short overview of the discussion for today. We will be having a short modeling statement about the structure information. Then we would proceed to modeling by defining properties, and then we will use a feature from IDA Civil, which is RC frame or box culvert wizard. Then after going through with the box culvert wizard, we will be inspecting the boundary conditions that were assigned, then the loads that were applied, then ultimately we will be performing the finite element analysis for our box culvert. Then after the analysis, we would have to extract the results or check it, and then we will use this data for our design of box culvert components. So again, for those that are first time to attend the webinar for Midas Civil, I would like to tell you that Midas Civil is the specialized program of Midas softwares for bridge and other horizontal structures. The types of bridges that can be modeled using Midas Civil are various, from the conventional bridges such as this box culvert, frame bridges, slab bridge, precast or integral bridges, as well as the steel box girder bridges. It can be modeled using Midas Civil. When it comes to stage segmental bridges like pre-cantilever method of bridge construction to incremental launching to movable scaffolding up to the precast segmental type of construction of bridges, it can be simulated using MIDASIT as well. Even complicated bridge structures such as cable stayed, extra doors, and suspension bridges can be modeled and analyzed using MIDASIT. So, moving on, let's see the power of MIDASIT in modeling, analyzing, and designing simple structures such as box culverts. So let's start by defining our box culverts. So first is just define culverts. So according to our code, culvert is a structure in the form of pipe or box below road level used for conveying stormwater runoff. But quite frequently, it is also used as cattle or pedestrian underpasses. So here is an example of a culvert. You can see that there's water runoff underneath it. Then, when you say box culvert, it is just literally four-sided culverts. So you may have heard of it like RCPC or reinforced concrete pipe culverts or box culverts as RCBC as reinforced concrete box culvert. Typically, it is embedded so as to be surrounded by soil. So it can be made by pipe or reinforced concrete or other material. So currently, most box culvert installations are provided in precast form due to the huge amount of time that are reduced for production and construction. For today's session, we will be utilizing our feature which is called the RC frame or box culvert wizard. So here are some of the application of our wizard that will be used for today. So RC frame or box culvert wizard can be used in rigid frame bridges, also known as ramen bridges. So these are bridges that consist of superstructure supported on either vertical. So if it's vertical, it is classified in the wizard as RC frame. It looks like this. Then if the columns are slanted, it is classified as pipe type bridge, like this one. So this is where the superstructure and substructure are rigidly connected to act as a unit and are mostly economical for moderate or medium span bridges. So aside from this two, box culvert wizard is also used, of course, for box culvert. So this is what we're gonna use for today, box culverts. So we will get to know more about our RC frame or box culvert wizard as we go on. Let me tell some of the structure information for our project for. So you can see the structure information either in the general notes for the structure or this is the one that you can provide after providing the design for this. So what we ultimately need is the material data for the concrete, our reinforcement that we'll use, and the soil that surrounds our culvert. So we need the reinforced concrete unit weight, then the soil fill unit weight if we have, then the backfill angle of internal friction, and water unit weight if there's water surrounding the box culvert, and of course the modulus of subgrade reaction for our supports. So if you don't have the data yet for this, you can assume values, give an educated assumption, and then you can check for the actual values in the site before construction to verify your design. So here is the elevation view of our box culvert that we'll use. So we have two span 6 meter of box culvert and then we have a wing wall of 3 meters by 3 meters. Then here are some other dimensions that we need. Then here's the plan view of our bridge. So as you can see here are the wing walls and it's inclinated or skewed in a 20-degree angle. Then the length or the cross-section length is 14.4, the width. So here's the separation of the cross-section. So we have 12 meters for the carriageway, then zero point 0.8 for the sidewalk, then for the barriers we have zero point 0.4. So ultimately, after we model this using the information that we're given, we would have a 3D model like this one. Yeah. So maybe we could start. So open your Midas Civil. If you open your Midas Civil, you can see that there's always a news feed here when it is connected to the internet. So you will know what's new with Midas Civil. And then you can register your license here. So you'll need to input the PKID and then the product ID of your license. Then you can see the version of your software here. Then you click on the little triangle beside the help and click on about Midas Civil, and then you can see which version it is using. So as of now, you can see that there's a latest version that is already released, Civil 2020 version 2.1. So let us create a new file. You can create a new file by clicking the icon here or Control N. So firstly, you need to save this one. So Control S or use the icon here for save. Then make sure that you have a separate folder. So RC box filter. Let's name it as such. So we need to include this in a separate folder because Midas will also um, creates temporary files, especially when you are doing design and analysis. So the extension file name for MIDASIT is .mcb. Then after that, make sure that the units are set. So we can set the units here, either SI or English. You can um, decide, and then if so, there are many ways on how to model here in MIDASIT. So aside from creating from scratch, you can also import from other types of files like from AutoCAD DXF. So if you have the layout already in AutoCAD DXF, you can just import it here. You can import tap files, TAD files, nested files, and then loose as stat files. But now we will be creating models from scratch. So the first thing to do is create the material property, which we have defined earlier to be, let's see, to be grade C5000 with compressive strength of 35 MPa. So let's go back again to our MIDASIT. So let's go to the properties tab and then create the material property by clicking the material properties. So let's add a property here. Then as you can see, there are different types of design that can be used. You can create steel model, steel concrete model, steel reinforced concrete model. So whenever you choose the material data, make sure that it is the type of design that you will have run in this members. So for now, we will use concrete design for our whole box culvert. So we need to include it in the concrete. So after that, you can see that steel is disabled since we use the type of design as concrete. And then the standard data for our concrete standard codes are being shown. So we have a variety of standard codes that can be used from ASTM, which is the usual ones that we use here in the Philippines, up to CNS or AS. So usually we update this if there are new codes that were released. So for now, we will use ASTMRC, and then from the database of ASTMRC, we will find the grade C5000. So grade C5000, as you can see, if it is from the database, the name is automatically filled up as well as the material ID. Material ID, as we go on through the modeling, you can see that it is the code that is used for the whole process in the MIDASIT. So it is okay to duplicate the name of the material data. However, it cannot duplicate material ID. So when you click on the database for ASTMRC grade C5000, you can see that the properties are being filled up automatically, like the modulus of elasticity, Poisson's ratio, thermal coefficient, weight density, as well as mass density. So properties for steel and concrete are almost the same. You have the liberty to use either the weight density of your material or the mass density. So whichever suits your analysis or your design, it can be iterated here. Then you can also input plasticity data if you have functions for that as well as inelastic material properties. Then you can also include separate damping ratio for each of your materials. So now that we have our material data, as you can see that if it is from the database, you cannot modify the values for the properties. However, if you turn it back again to none, you can see that modification for these values are now available. So here's just some tips for you. So you can modify it according to the values that you want. So if you want to cross-reference them and then include a little bit of discrepancy or avoid this, you can modify it here. So let's bring it back again to ASTM-RC. Then click on OK. So there are two executions here, apply and OK. Apply executes the command without closing the dialog box. However, OK executes the command with this closing the dialog box. So as you can see here, it is included in our list of the material properties. So let's close this one. Then we can see here in the works tree, everything that we have inputted in our model is reflected here. So we only have one data that is inputted, which is the if we use our box convert wizard. So we can find our box convert wizard here in the structure tab. So as you can see, you can include here the structure type. Then there are a lot of features that you can choose from. But now we will be utilizing the RC frame or box convert wizard. So before you click on the RC frame or box convert wizard, make sure that the units that you have selected are the ones that are available in your references. So for me, I will be using kilonewton and then meter. So let's click on RC frame. So RC frame or box convert wizard is consisting of three tabs. First is the longitudinal tab, then the transverse tab, and then the loads tab. So in the longitudinal tab, you can find the data that would be used for the span and the dimensions of your box culvert. So first, we need to decide on which structure type we are going to use. So you can model both two-dimensional and three-dimensional frame bridges here. So for our model, we would be using three-dimensional model. And then for the type of bridge, we have the normal type frame, which is like this, and then the pi type frame, which is the monolithic bridge with slanted side columns, and then the next one is the box culvert, which we are going to use. So as you can see here in the guide, we have the thickness of the pavement, the height of the soil above the culvert, and then the span length, and then the thicknesses inside of the culvert, as well as the wing walls. So basically, here are the data that we are going to need in order for us to accomplish the box culvert wizard. So after that, after the structure type and the type of bridge, we need to define the material that we will use for the box culvert. So the material that we will be using is the grade C5000 that we have defined a while ago. So in case you haven't defined anything yet, you may define it by clicking on the tree that's beside it and then define. So you can define it here. And then you need also to define the size of the plate element. So the size of plate element comes into picture only for 3D models. So the size has to be decided based on the accuracy of the results expected. Um, so for example, we have our plan and elevation of our So based on that, we can see that 0.5 meter is the right size or the or this size of our mesh would suffice for the analysis that we need as for the finite element. And then we need also to define the span length. So this is given in our plan and elevation a while ago in our presentation. So 2 6 meter span of culverts. Back again with the size of the plate element. We need to make sure that the mesh elements does not look elongated while choosing the size of the plate in the next tab, which is the transverse tab. So basically, mesh size should be 1:1 ratio with transverse and the longitudinal for good results. So after that, we need to define also the wing wall. So you can decide if your box culvert will have a wing wall or not. So if you decide if it's gonna have a wing wall, we can include the thickness here. And then after that, we also need to define if it's skewed in the longitudinal direction. So mine is skewed in 20 degrees. So I put it here. And then if the plan of your box culvert is not straight, so you can include the ratios of your bridge here. So just check on the ratios, then include the ratio signs here, and then you can define if it's convex or concave, and then based on that, the walls of your box culvert can be set into radial type or parallel type. So ours won't be circular, so we don't take this one, so uncheck. And then the other dimensions, so basically we need to define the thickness. So the thickness of the top slab and the thickness of the walls in between, and then the thickness of the outer walls, and then the thickness of the bottom slab, and then the haunches and the corners of the box culvert. We also need to define the height of the soil that would be above the box culvert, which is the H2, so H2 soil, and then the thickness of the pavement. There are times when there is no soil above the box culverts. That's why the P here is equal to the H2. So meaning there is no soil above our box culvert. So in AASHTO, there are or AASHTO standards, there are minimum wall thickness says on all over the box culvert. So since this is a AASHTO, the unit system is in English, so the minimum thickness, so I'll just dictate it, for all the box culvert is 8 inches, and it can be increased with the clear span length. And then the minimum slab thickness for culverts with span of 6 to 8 feet is 8 inches. The minimum top slab thickness is 9 inches, where the minimum bottom slab thickness is 10 inches for all the culverts with spans not larger than 8 feet. So there are rules like that in a AASHTO or in our local code. So you need to satisfy that. Then if you have a preliminary dimension of your box culvert, then you can include it in your model for analysis and design. So next would be the transverse tab. So in transverse tab, as you can see, we also provided the dimensions for this, for the cross-section of your bridge. So there are three types of the cross-section of your bridge in the transverse direction. So the first type is seen here, which is on both sides it has barriers and sidewalks. So for the second type, this is where on the left side of your bridge you have barrier, and then on the right side you have median strip. And then on type 3, you have median strip on your left side and then barrier on your right side. So as I said a while ago, the size of the plate element should be um, ideally 1:1 for the transverse and the longitudinal direction. So you remember from the longitudinal tab, we defined it as 0.5. So now in transverse, we will also define it as 0.5. So these dimensions are given in our drawing for the structure information. And then this one is only applicable for the supports of the pi frame. So the supports of the pi frame usually are transverse fixed support. So you need just to include the location of that. But for culverts, you have two options, general and compression only. Compression only is applicable for two-dimensional analysis of box culverts. So we are only left with the general spring type. So we also need to define the modulus of subgrade reaction so that we can so that we can include it in our supports for the Culvert. So this one is also given from our geotech. So this is based on the soil that we have. So it is the modulus of subtlete reaction, which is 1965.9 kilonewton per cubic meter. And then the length of elastic link is usually half is taken as half of the base slab thickness. It is basically to induce the eccentricity to the support of the springs. So this is because in software modeling, the dimensions are generally considered center to center. However, in reality, soil offers support at the bottom of the slab and not at the center. So in order to replicate this, elastic links are used. So we need to define the elastic link length. So that is the basic idea of getting the length of the elastic link. So moving on to the next tab, which is the loads tab. So as you can see, we need to define the load combinations that will be used for our analysis and design here in the load tab. So both factored and unfactored load combinations are automatically generated after we executed the box convert resort. So I chose ASHA-LRFD 2002, and then we also need to define the moving load code. So moving load code, here are the options. We have the ASHA standard, ASHA LRFD, PEN.dot Canada, BS Euro code, Australia, Poland, Russia, South Africa, Korea, India, and for the transfers. So we will be using ASHA LRFD. Then click on OK. By the way, the choices for the load combinations are here. So we have the ASHA standard, ASHA LRFD, CAN, and then IRC. And then all of the other loads have checkbox beside it, so we can activate and deactivate these loads. So first one I activated is the self-weight, and then the other one is the pavement. So we only need to define the weight density of our pavement. The thickness is automatically computed from our from our longitudinal tab, which is the dimension P, so 0.25. And then we have also the load for the soil. So we included the load for the soil, which is 20 kilonewton per cubic meter of the weight density. So I checked the weight density of the soil that I've given a while ago. So it is only 20 kilonewton per cubic meter. And then the axial angle of internal friction is 35 degrees. And then the unit weight of our surcharge for the water is 10 kilonewton. I mean 12, sorry. 12 kilonewton per cubic meter. And then this one we need to check. So we'll just assume it as such. And then the underground water, it can be seen from the hydro survey of your bridge. So you can also assume this value. And then there are loads for barrier. So we have barrier and sidewalk in our transverse, if you remember. So you can check on it. And then you need to define the self-weight of that. So this would be equivalent to the shape of your sidewalk multiplied by the unit weight of the material that is used for the barrier. Sorry. Weight unit weight of your barrier and then the shape of your barrier. So this is in kilonewton per meter per unit length. And then same with the sidewalk. So the sidewalk, its weight density and the thickness. So this one is, let's keep it as is, 0.3048 And then for the crowd load, you may look in the pedestrian loadings from AASHTO or DZCS, so you can see the data for that, which is 3.6 kilonewton per scrum. And then, as soon as we have defined the moving load code, we can already decide on the design live load. So based on the standard that we have chosen, which is the AASHTO LRFD, the standard that we have is the AASHTO HL93 truck and HL93 tandem. So I'll check on both, and then we also need to define the eccentricity that will be used for the surface lanes. So this eccentricity would be used as a reference axis when the live load is applied eccentrically. And then the other loadings, which is the system temperature and the temperature gradient, I chose not to include values here, but you can also assume the system temperature and temperature gradient for your temperature for your box culvert, since temperature loads are essential for bridges that includes water that pass through it. So we need to have the data for this, and then can also include shrinkage strain, which is loaded as element temperature load as well. So if you have included all the data for the longitudinal transfers and the load tab, you can save this file as a wizard file. So we can do 6 span two span 6 meter box culvert. So you can save this wizard file and then use it again in your future projects. So that's the beauty of using box culvert wizards, because it saves you time. So it provides more productivity for the users of MIDAS. So after all of this, we can now click on OK. So check it again before clicking on OK, because as soon as you click on OK, it will generate the model. So click on OK if everything is okay. So as you can see, we have created a box culvert here. So now we can inspect the things that are automatically generated using our RC frame or box culvert wizards. So firstly, we have plate elements, 2088 plate elements. And then for the properties, it introduced 6 thicknesses, so 0.56, 0.42, 0.28, 0.405, 0.53, and then 0.5. For the boundaries, so you can change the view into hidden view if you want to see the wireframe. So you can see the boundaries here. First is the support. So you can display the supports here. So as you can see, all are fixed. So we can see that the support is fixed when. So basically, supports are just binary type of support. So it is either free or fixed. So it consists of 6 triangles. So each one represents a degree of freedom. So if all of those triangles are colored green, it means that in all of its displacement and all of its rotations are fixed. So you can also see it by viewing the table format of the supports by right click and then right click on the supports, then click on tables. So as you can see, displacement along XYZ When it's 1, meaning it's fixed, and when it's 0, means it's released. So dx, dy, dz is displacement, rx, ry, rc is rotations along xyz, and then rw is rotation for warping. So if that is restrained, it would introduce a equivalent torsional moment so that it would be restrained. So let's close on that. Basically, RW is used mainly for restricting lateral torsional buckling. And then the next one is point spring support. So you can also see it here. So as you can see as dx, if you remember quite clearly, 19635.9 is the one that we have assigned in our box Culvert wizard a while ago. So it is used as stiffness here. So close this window. Then we can display it here. As you can see, it is included in the internal wall of our box culvert. So the restraints are on the x-axis, and then on the middle, it is restrained in xy, so that it would um, have a support so that it won't move around this structure inside. So it won't slide um, longitudinally and transversely. That's why we included the point spring support. And then other than that, there is also an elastic link. So length of elastic link is just so little because we defined it as 0.14. So if you want to know the distance between two nodes, you can click on F4. So there's a query dialog box. You can click on the first node, the second node. So distance from node 1 to 2 would be 0.014 meters. So that is the one that we have defined a while ago for the elastic length. So if you look closely, the the elastic link seems to be the support of our box culvert. So in order for us to imitate the behavior of the soil, we must look on the elastic link tables so that we'll know where the stiffnesses of the plastic links are. So as you can see, it is included here, and it is automatically calculated by MIDASIT. So the values of the stiffness here are based on the location of the nodes that are in the bottom slab. So if it is located here, the tributary area of that node would be the stiffness, would be the basis of the stiffness of the node here. So basically, due to the nature of the soil, it cannot resist against tension. Therefore, our supports here should be compression only, which is reflected in the stiffness that are assigned in our elastic links. So aside from the boundary conditions, we can also look into, so I will display this. We will also look into the loads that were assigned in our model, which are static loads and moving loads. So first is the dead load. So we have self-weight, and then we have the loads for our sidewalk and the barrier, which is assigned as pressure load. So after the DC dead load, we also have another type, which is for the wearing surface. This is from the pavement. And then we also have horizontal earth pressure with water and without water. So let's see first the one with the water display. So you can see that it is assigned in the wing walls and on the sides of our culvert. Also, the shape of our load, as you, if you can see it clear, you can see it, it is triangular. So the same application is done with for the earth horizontal pressure without water. It's just that the values are different from each other. So they just deducted the unit weight of the water. Aside from the horizontal earth pressure, water pressure or hydrostatic pressures are also assigned using pressure loads. So it is also assigned on the area, not all throughout, but because we have included the um, negative, negative, negative elevation. So there are parts which doesn't have water pressure. This one, almost the first mesh doesn't have the water pressure. So there are two types, one from the side and the other one is for the bottom, for the buoyant forces. And then the next one is the crowd load, which is only applied on the sidewalk of our bridge. So after the static loads, we also have moving loads. So this is in accordance with the ASH to LRFD. So according to ASH to LRFD, and then we have three traffic surface lanes. So let me just undisplay this one so you can see the traffic surface lanes. So if you want to see it, you can click right click and then display. So this would be the lane 1, lane 2, and then lane 3. So if you are analyzing box culvert two-dimensionally, there is a separate provision for that in our code, and ASH the code as well, that you um, need to consider. Also, if there is a soil above your box culvert, you also need to have another provision for that because the distribution of the loads from the top of your pavement going to your culvert will be different. Then you also have negative support, negative moment supports, which is in our middle walls, and then our two vehicles, the truck and tandem HL93. So these two vehicles were included in one vehicle class. MVLC vehicle class, and then the tandem and then the truck load are also included in our vehicle classes. Then after that, it automatically generated a moving load case. So um this is the feature of MIDAS that combines the traffic surface lanes and then the vehicles in order for them to create a loading condition that imitates the moving load. So you can include here the multiple presence factor of your vehicles. Also, um, let me show you the loadings for the truck and tandem. You can apply here in the truck and tandem load dynamic load allowances. Also, lean loads are included in the standards. So yeah, dynamic load allowance is already included. So basically, we didn't do anything after the RC Framebox Culvert Wizard. Now we are ready to analyze this model. Let me display the negative moment supports. You can analyze it by going to the Analysis tab, then clicking F5 or this shortcut here. So now we will be performing analysis. Most of the time, engineers are intimidated by finite element analysis, especially if they have a big project. Because firstly, modeling takes too long, and then analysis also takes too long, and then they cannot extract results easily. But as you can see, modeling is already handled by MIDASIT, so it makes them easier for them. It makes the MIDASIT makes it easier for them to model box culverts like this in finite element. And then also the analysis. Let's see how many minutes it would take for it to form element stiffness and load matrices to conduct static analysis as well as the moving load analysis. So this length of time that you use in performing analysis takes into consideration the number of plates that you have. Of course, the more number of plates, the longer it will take. Also, the hardware that you are using, and then the number of iterations that you need in performing your analysis. So aside from static analysis and moving load analysis, you can also add other analysis in just one model. You can always see the operation that MIDASIT does here in the message window. So as you can see, it conducts moving load analysis, and it is now in the plate element force moment group number something over 2088 groups. So as if you can imagine, it conducts analysis for every plate that you have. So yeah, it would obviously take time, especially when you have bigger projects other than this. Now that the analysis is done, you can see how many seconds it took. So it took me 262.28 seconds to run this. Now, before we move to the design part, let us inspect the results. So click on Results tab. Let us see the load combinations that were automatically created using our box culvert wizard. So click on Load Combination. So as you can see, we have General tab and then Steel Design, Concrete, SRC, Composite Steel Girder Design tab. So for the General tab, here is here are the load combinations that will be used in extracting the analysis results. So we have strength load combination, service load combination, and envelope load combinations. So this one is automatically created, but you can also create a new one by inputting the name here. And then, so for example, you input, say for example, load combination 1, and then click the load case that you would want. So for example, dead load, and then could include the factor, then include another load case, say for example DW, then include the factor again. So here's how you can do it. And then for the other tabs, so still design doesn't have any load combination on it. And then for concrete design, which we will use in the design part, it already has the load combination. So in order for you to create a load combination for the design portion, you can manually input here, or you can copy from the general tab. So go to the general tab again, and then choose the load combinations you would want to copy, and then choose where you want to copy it, and then click on copy into. So that is how it is inputted here. Then aside from that, if you want to auto-generate loads other than the one that we have defined a while ago, which is from ASHTO LRFD 2002, you can click on auto-generation, and then choose a design code. So we have from LRFD 2016, 2012, 2007, and then from other codes. And then here are the load factors that you can use. So maximum or minimum, or you can use both. So if you want to use this, just click on OK. But since we already have our load combinations, I'll just cancel this and then close this load combination. Now let us see the reaction for our model. So you can either click on you can show the reaction forces, you can also search for reaction, and you can also see the soil pressure if you included soil pressure. So let's see the reactions. So for the actual reaction, and then for the values, let us click on the three dots beside this, and then just display the minimum and the maximum values. Absolute maximum value, then click on OK. Then let us also show the legend. So let's go to our frame view to see where this is. So it is easier to see here. So the minimum reaction is on node 1194. The maximum reaction is on node 1208. So if you want to change the unit, it could be done. So the forces, the reaction are also changed if you change the unit here. So the reaction 10.9 negative, and then for the positive one, 10.9 as well. So there's it. There it is, the red one. And then you can also view the deformed shape or the displacement contour of your model. So let us see the displacement contour. Choose a load case or load combination, and then click on apply. So as you can see, here are the maximum values. Here is the contour. Aside from this one, this this contour that you can see, it could also include plate cutting diagrams along your box culvert. So click on plate cutting diagram. You can either choose cutting lane or cutting line or cutting plane. So I will be use cutting lines. So you'll just need to define point 1, and point 2, and then add it for your cut line. So let's create one again for the transverse here to here. You can add skewed lines aside from straight lines here. Then click on apply. So here are the ones that I've created. So let's change this into so we can see the values. So if you want to view the conventional graphs, you can click on reverse and then click on apply. So you can see here. Then aside from the deformations, you can also look into the plate forces and the plate moments. So let's see the moment about x-axis due to the load case dead load. So you can either choose element or average nodal. So average nodal averages the moments on the plates that are connected on that node. Click on apply. So here are the maximum values. You can also see on the legend the values that are represented for each color. So aside from that, you can also see the diagram for the cutting lines that you have prepared a while ago. Let's click on apply. Then you can see here the moment diagram of the cutting line that we defined here. So let us see if it is average nodal. Click on apply. As you can see, it changed here. So those are the usual values that you need for your calculations. So aside from that, if you need beam, I mean plate plate forces for for example other design calculations that you would need. So if you need to have we have this feature which is the local direction force sum, which provides internal forces on a selected line or plane in a beam, plate, or solid elements. These resultant forces and the acting point are calculated on the basis of all the nodal forces included in the selected plane. So if you need a detailed analysis for a specific part of a structure, this function calculates the member forces for the structural design. So you can activate it here in the results tab, then local direction force sum. And then just input a direction. So can either choose load cases from the static load cases or the load combinations that you. So first position, then last position, then add. So you can see that there is a result output for that. You can either calculate for just the single load case or for all the load cases or load combination. So if you click all load case combination, a text output would be given to you. So these are all the design forces or member forces that you may use for your structural design. So this one can easily be imported in your Excel spreadsheets or MATCAD. So just create a position and then choose whether which load combination or static load cases that you need. Then you can use this text editor. So that's it for the local direction force. Close this one. And then let us now move on the moving tracer. So moving tracer option is more on the moving load analysis. It will trace and display the vehicle loading condition that will yield the maximum and minimum effect of these components that you need based on a certain location. So if you click on moving tracer, you can trace loading conditions for maximum reaction, for maximum displacement, for maximum thrust and beam forces, also for the plate forces, which we will do. So moving load tracer and then plate forces and then moments, and then click on the key element or location. And then for the parts, you can either choose IJKL or the side 1, 2, 3, 4 in a counterclockwise direction. And then click which component you want it to yield. So you can yield forces on x axis, y axis, xy axis, or moment on x axis, y and xy axis, and then shear for x and y axis. So you can click on apply after defining the key element and which moving load keys you want, either maximum or minimum. So here is the loading condition that will yield the maximum moment about x. So here is the lane loads and then the vehicle loadings. So this can also be converted into static forces. So to convert this, you can click on write min max load to file, and then for the conversion, you can also include centrifugal forces and or braking forces. So you need to define the design speed and the radius of curvature and the factors and direction for the centrifugal force. And then it will give you a text file or MCT file. So all you need to do is copy all of this code, close this one, and then go to the Tools tab, open the MCP command shell, and then paste it, and then run. So you'll be running again the analysis for that. So let's just click on yes. Then close this one. As you can see, it introduces 5 load cases, which is which are nodal loads. This represents the moving load condition that will yield the highest moment about x on node based on node 116. Centrifugal, vertical, and then horizontal, and then the braking force, and then the acceleration force. So we need to reanalyze this again for us to continue with the design part. Let me just reanalyze this one. uh, we analyzed it again, and then we are ready for the design part. So here in the design part, the only preliminary data that we need are the locations of the structural design that we will do. So we need to do that by creating domains and subdomains in our model. So you can create domain and subdomain here in the Node and Element tab. So it has meshes already. We need to define the domain. A domain is our locations of the elements that are created using the meshing. So we need to define, well, we'll just do design for the top slab, bottom slab, and the sidewalls. So we can undisplay this part. So just select this one and then click on undisplay. So now we will be defining a domain for the top slab. So create all, select all the elements on the top slab. Plate elements on the top slab, then include top slab. Then add, and then for the bottom slab, select all the elements, plate elements on the bottom slab, and then include bottom slab. Always use the element type plate. And then for the sidewalls, let us unselect this middle one and then include sidewalls. So we already made 3 domain, top slab, bottom slab, and then the sidewall. Now for each domain, we can include subdomains. So subdomains are the unit area of mesh elements. So these subdomains will be the one that we will use for our design. So for top slab, let us just include about 4 elements for each. So top slab and then subdomain. So we need to have elements on the ends, on the middle, and on the center. So for the top slab, let's name the top slab end elements as PE, and then member type plate beam. So this plate beam, it would consider a slab design like one-way beam. And then for the rebar direction, so this would define the direction of our main bars and the main bar and the secondary rebars. So you can either choose the based on the local direction or the axis of your elements, or you can use the user coordinate system, but if you haven't defined it, it would be the global coordinate system. So we have direction 1 here and direction 2 here. Or you can define reference axis. So if you want to define reference axis, this would be based on the right hand rule. So just select elements on the end of your top slab and then add. And then we will do the same for the mid top slab mid. Same plate beam element and then just include it 4. And then for the mid, include 6 elements. So I mean center. So these design locations are depending on the engineer that would design it. So you can design it here. For example, all of the plates at the end, you can design it all. You can design all the plates at the mid. You can also design all the plates at the center. For simplicity, I just included some here, six I mean 6 elements here, 4 elements on the mid, and 6 elements on the center. So we have the subdomain for the top slab. We will do the same for the bottom slab. So click on top bottom slab, then define subdomains. So same with the top slab, we will be defining a location for the end, bottom end, for the bottom end. Don't forget the member type, plate beam. Then 6 on the mid. And then for the center part, 4 on the center part. And then for the side walls as well. Close this one for the bottom slab and then create another one for the side wall. So subdomain, but this time instead of plate beam, we will be using plate column. So plate column considers abutment or sidewall design. Like column, it will consider actual force and then the moment. So for sidewall, we need, let's unselect everything. We need elements from the top. Let's just select 2. Okay, so let's select 4. Then rebar direction, the current UCS. Then add. And then sidewall mid. And then sidewall bottom. then close this. So we have defined subdomains and domains. We can now proceed with the defining the domain and subdomain. We need to analyze it again, and then now, after analyzing it for 193 seconds, we can push through with the design. So go to the design tab and then choose design code. So we will be using HTLRFD 2012 for RC design. And then under RC design, we would be inputting plate beam data for design. So we need to have two plate beam data and then plate column data. So for plate beam data, we need to input the subdomain. So here are the available subdomains for the plate beam design. BC or top and bottom slabs for the center and zenith. So for each of these, we will be inputting a plate beam data design, plate beam data. So BC. Then for the plate force, there are two options, either element and then average nodal. So for element, it uses the internal force calculated at each node of selected element. And then for the average nodal, it uses the average internal nodal forces of all the plates that are sharing the common node. So I will be using average nodal. And then the main rebar direction is for the direction of the rebar, main rebar, and the distribution bar. So either direction 1 or direction 2. So if you remembered, you have the it has a guide when you define the subdomain here, and you define the rebar direction 1 and then direction 2. So here, the direction 1 and then direction 2. And then you need to include a stirrups data. So this is optional. This is the size of the bars that are selected. So P16. Say for example, 4 pieces. So this stirrup data is per unit length. So it's the number of shear reinforcement per unit length. If you want to change the sizes of your rebars, you can change it in the Tools tab and then Preferences, Design, Designer Load Code, and then Concrete, and then Material Code. I am using now Uni RC. You can also use ASTM RC. So if you use ASTM RC, go back again to the design, then plate beam data for design. So BC again, average nodal, then it would be like this, the sizes. For change is into ASTM sizes. But me, I prefer the uni sizes. So I will change it back to uni sizes. So BC, then P16, say 4 pieces per meter. And DT and DB is the concrete cover for the top and bottom of your slab. So let me put 75 mm, then add for BC. Same would be for BE, BM, BC, PE, and then PM. So we have data, plate beam data for design. Now we would be including plate column data for design. So it's basically the same, but this would be applied to the column design of our structures. So average nodal, direction 1, then input stirrups data as well. Then concrete cover. Concrete cover is from the surface of the top or bottom of your plates up to the center of the main rebar. So surface to the center of your main rebar. Then after that, if you already have plate beam data and plate column data, you can proceed with the concrete code design. So we will be using the plate beam design. So plate beam design, you can see here that it is now designing a plate beam design in the subdomain TC, BE, BM, and then BC. So now the results are available. Just expand it. You can see here that the status are okay. Major directions are direction 1. Here is the required area of steel for the positive side, negative moment, which element yields the maximum or most critical, which node, and then the load combination that results in the critical moment, and then the maximum factored bending moment, and the bending moment resistance, automatically calculated by MIDASIT. And then its ratio, DC ratio. So it would also give you the maximum or the most critical element and node that produces the maximum shear, which load combination, and then the maximum factored shear, and then the shear force resistance, the ratio of BU and BR, and then the required area for shear, and then the stirrups. So for every subdomain, you can see here the results. So let's select one first, say BC, and then click on the detailed result. So you can see here on the detailed result the definition of load combinations with scaling up factors that is used for the RC plate beam design. So here are all the load combinations that were used. Then you will have the data for RC plate beam design according to ASH LRFT 2012. So for the subdomain BC, it's designed as one way, thickness used, and then the elements, and then the reinforcement pattern. And then it would analyze. It will design according to the positive bending moment capacity, giving you required reinforcement. So we have 8 trials here, and then you can see the assumed area of reinforcement for the top and bottom and the ratio. Sorry. So you have here the status if it's no good or okay. So if you want to maximize the use of your rebars, you can use this one. Or if you want to be safe, you can use this one. The units is in kilonewton and mm, so square millimeter. And then checking for the moment capacity is here. Aside from that, aside from the positive bending moment capacity, it also design for the negative bending moment, if it has negative bending moment. But this one, it's just minimum. And then for the shear capacity as well, it designs based on that. So you have shear parameter, then shear strength of the concrete, the computation for the stirrup, the shear strength of the reinforcement, and the tension forces in the longitudinal reinforcement caused by shear. So you can see if it's okay or under reinforced like this one. So here is the plate beam design of MIDASIT in detailed report. So you can save this or not. You can also see the graphic result. So here is the graphic result of MIDASIT. It um, presents the design condition, the section diagram, the required rebar areas, and then the stirrup spacing. Also have the bending moment capacity and the shear capacity. So basically, it is a summary of the design for the particular slab. So if you select all of this would be seen in the detailed and the graphic analysis. I mean, presentation of the results. Now let's go on with the design for the column. So we have already the plate column data for design. Now we can design for the plate column. So it only has 3 subdomains, so it would be much quicker. It's already done. Then click 1, so we can see the detailed calculation. This is the summary, same as the one before. Let's see the detailed report. So this is for plate column design. Here are the load combinations that were used. And here's the start of the plate column design. First, it gives you the design forces that were used, and then the reinforcement pattern as well. It shows you the checking for the positive bending moment capacity. So it doesn't apply here for the positive, and then for the negative bending moment, we have here computation for the required reinforcement. So here are the ratio and the assumed area of steel for the top and bottom. And then for the shear capacity, here is the checking as well. So basically you can choose the assumed, you can choose to include or to use the assumed area of steel for the top and bottom for your reinforcements based on the ratio or the design that is done by Midas. Just take it down, take 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 note of it, and then you can run it for checking afterwards. So after the column check, let's close this one. Let's see the graphic result. So here's the graphic result. Same thing, it has the design condition, the bending moment capacity, and then the shear capacity checking. So aside from the design, you can also check your um, your reinforcements if it um, if it passed the recommendations or the requirements of the code that you use. So let's close this one for the column design. Let's let us include report data input for plate beam. So we have here center to center spacing of 25, size 116, then size 216, concrete cover from top 75, then single layer. You can have up to 3 layers of this rebars. For the bottom bars, we have same 25 spacing, size is 16, and then the distance from bottom is 75. Then for the distribution bar, I had 25 spacing, center to center spacing, and then the size is P16. Then use that for the plate beam data for checking. So include the subdomain name, then average nodal, then which direction is the main rebar, then the rebar data. Then if you already have rebar input for plate beam and then plate beam data for checking, you can now have concrete code check for plate beam. So we only have one subdomain with rebar data. Let's look into it. So you also have same thing. We have the status, the recommended reinforcement area, the factored load, the the factored moment, the moment resistance, the ratio of the resistance to the moment, same as the shear, and the ratio of the shear. So here is the detailed calculation. So for plate beam checking, here are the load combinations that were used. And for the plate beam checking, it has reinforcement pattern. Here's the diameter and then the pattern of the reinforcement that is recommended by MIDASIT. And then it has checking for positive bending moment capacity, checking for negative bending moment capacity, checking for shear capacity, and crack control checking, as well as shrinkage and temperature reinforcement checking. So as you can see, the design portion of our RC design is very extensive that you can use it for submissions of plans, and it could also help you design very quickly. You'll just need to verify the results or maybe check some of it so that you can also understand how the software works. So in the handout that is attached in your GoToWebinar options tabs, handout tabs, you can find all of the detailed step-by-step procedure and some explanation, some more extensive explanation of the things that I have presented now until the design part. So I also included an appendix here so that you can fully understand how MIDASIT works. So for example, the forces here and how they affect each of the members. Then stresses as well. So here are some of the stresses that are induced. So I hope this presentation helps you in your projects, especially for box Culvert. So if you have questions, don't hesitate to email me at phinquiry@midasit.com. I hope you support future Midas events as well. Thank you very much and see you on our next webinar. Be safe. Bye.